Okay, so we're back to this new coordinate systems back in 11.7. So I can get to a point in space using rectangular coordinates, x, y, z. I can also get there using what they call cylindrical coordinates. But check this out. They're going to look real familiar to you. Watch this. R, theta, and z. So what the hell is that? That's called cylindrical coordinates. That's the phrase. It's a cylindrical coordinate system. I like to use this phrase, 3D polar. And maybe you know what I mean by that. What I mean by that is the x's and y's are kind of switched to good old r's and thetas. And then the z is still the same old z, height, coming up out of the xy plane. So I don't really like to use the word polar. It's not really accurate. Polar coordinates are a two-dimensional coordinate system, r and theta. You can convert x's and y's to r's and thetas. That's a two-dimensional coordinate system that we've discussed. X's and y's can convert to r's and thetas can convert to x's and y's. That's rectangular coordinates and polar coordinates in 2 dimensions. But the same idea in 3 dimensions we call cylindrical coordinates. The z is just the z, but the x's and y's turn into the r's and thetas. So how does that show up in this picture? You move around the xy plane in your polar coordinate fashion. You rotate this angle theta, step out this distance r, and then just go up z, you know? So it's still just the good old up z. So cool. So that shouldn't be too hard or too new. It's just 3D polar is my phrase there. This is brand new though. You ready? Spherical coordinates. Spherical coordinates is brand new. It's very cool. I like it. We're going to use it here the next few days to integrate stuff. And we're going to integrate stuff in. We're going to do triple integrals in spherical coordinates. But first, we got to learn about spherical coordinates. Spherical coordinates are rho. That's the Greek letter rho, theta, and phi. By the way, the theta is still the same old theta it was back here. But rho is this new sort of 3-dimensional stick from the origin out. Theta is this angle we rotated from the positive x-axis counterclockwise. And phi is now a new angle measured from the z-axis rotated down. So I can get to this point, and I'm going to call it rho, theta, phi. And I can get here by doing what? What the hell do I do? I rotate over an angle called theta. That's the same theta it was up here. I put a stick out there from the origin out to the point, and that distance is called rho. And that stick is rotated down from the z-axis down an angle called phi. That's spherical coordinates. Just define spherical coordinates. Let me see. I wonder if you could tell me the name of this point in spherical coordinates. Now hang on. What is the name of this point in rectangular coordinates? Let's say that's a 5. So I think the name of this point in rectangular coordinates would be, what would the name of that point be in rectangular coordinates? 0, 5, 0? Right, because this is the x, y, and z axis. Okay, so what about in, well, let's just do one thing at a time. Let's do cylindrical coordinates. So in cylindrical coordinates, that's just r and theta and z. R and theta and z. Oh, guess what the z is?
5.
No, the z.
0.
Yeah, the z is still going to be 0 because it's in the damn xy plane. Okay, so it's r, theta, and z, but z is still going to be 0. So r and theta. I think theta is
5.
no, theta is the angle. I think the R is 5, right, the R is 5. The theta is the angle pi over 2, I think, 90 degrees, pi over 2. That's that point in cylindrical coordinates. Spherical was what I was trying to do here. Let's do spherical. I think in spherical coordinates, I need rho. Rho is kind of like a 3D version of R. I mean, it's this, R is this radius from the origin out, but R never elevates out of the XY plane. Rho gets to elevate up out of the XY plane, but, sorry, not in this example. In this example, I think the rho would still just be 5. The theta is still the same old theta. Here we are again. We're doing rho, theta, and phi. Theta would still be the pi over 2. It would still be the pi over 2. But what about phi? Phi is this angle rotated down. I mean, this rho sticks out, but it's rotated down from the z-axis. And we're sitting here in the xy plane, so what is phi?
Pi halves.
Yes, so phi is pi over 2. Maybe that wasn't the best example. That's interesting, though. It's just a point on the y-axis. Rectangular, cylindrical, spherical. That's a different. Yeah.
So, sorry, I didn't mean to interrupt you, but
well, go ahead. There's a lot more to say. What comes out of these pictures, of this picture, what comes out of this picture is a bunch of equations. We can sit there and we can derive a lot of relationships amongst these variables. You know, we already know that there's a right angle here, and we know that x squared plus y squared is r squared, right? I mean, there's a right angle there and a right triangle laying in the xy plane, and x squared plus y squared is r squared, and we use that when we convert to polar coordinates, so that's still true. But watch this. So what about rho? You know, there's a right angle right there. So r squared plus rho squared, no, I'm sorry, I screwed that up. R squared plus z squared, r squared plus z squared is that hypotenuse over there, rho squared. And that's true and cool, but hold on a second. What's r squared? X squared plus y squared is r squared. So in other words, here's another way to say this. X squared plus y squared plus z squared is rho squared. And that's true. It's sort of a 3D Pythagorean theorem. X squared plus y squared plus z squared is rho squared. Rho being this 3D sort of hypotenuse here. X squared plus y squared plus z squared is rho squared. I usually don't sit here and derive these. I mean, that one sort of did, but that's the easy one. There's what happens, and this is all in 11.7, where this is introduced. It turns out x is rho sine phi cos theta. Y is rho sine phi sine theta. Z is rho cos phi. I mean, those are handy formulas. Converting, we're going to be converting from x's, y's, and z's into this new spherical coordinate system. We need some of these equations. You don't have to memorize them. You can look them up in 11.7, and on test day, I'll give you these somehow. We're stumbling across. I mean, this is a nice, obvious one. I mean, whether you memorize it or not, this is good. These aren't quite as obvious. I could have helped. It's right triangle trigonometry that helps you prove this to yourself. I'm just not taking the time to do it, I guess. But you can play around and do it here. If you And you know, these are called spherical coordinates. Check this out. You know, what is this? We've been dealing with this a lot here and there. What is that?
It's a sphere.
That's a sphere, centered at the origin, radius 3. Well, now check this out. You just learned something here. If I'm converting into spherical coordinates, x squared plus y squared plus z squared is rho squared. So if I'm going to convert this, this is a sphere of radius 3 in rectangular coordinates, but if I convert him, he's rho squared equals 9. If I take the square root, he's rho equals 3. Guess what that is? A sphere of radius 3. So that's pretty sweet. Spherical coordinates are nice for spheres. Rho equals 3 is his name. Z equals x squared plus y squared is a paraboloid. Let's see, let's convert this paraboloid. So here he is. This is called a paraboloid in rectangular coordinates. Let's convert him. By the way, he's a real nice, hang on, here he is. He's a very basic, nice paraboloid. He's a very circular paraboloid, actually. Very nice, basic, easy paraboloid. And there he is in rectangular coordinates. Let's convert him to cylindrical. If you're converting to cylindrical, basically that means you're converting the x's and y's into r's and thetas. What would you do with an x squared plus a y squared? You call it an r squared. Guess what? That's a paraboloid in cylindrical coordinates. This is the same thing in cylindrical coordinates. This is his equation, and so z equals r squared is his equation. Let's convert him to spherical. Oh shit, I don't know about that. Let me think here. If I want to convert to spherical, what's z? Z is rho cos phi. I think I'll just do that. Z is rho cos phi. What the hell is r squared?
Rho squared, one is c squared.
You know, let's play this game, you know. I'm just going to do this on my scrap paper. I mean, this is how you play and convert, you know. R squared is x squared plus y squared. X, so now what did I do? I just converted r's back to rectangular coordinates. Well, I'm trying to get to spherical coordinates, so hang on. X is actually this. So x squared is rho squared sine squared phi cos squared theta plus y squared, which is this squared, rho squared sine squared phi sine squared theta. Watch out for your phis and thetas. Watch out for your phis and thetas. Look, you know what I'm going to do with this? I'm going to factor out a rho squared sine squared phi, and it leaves me with cos squared theta plus sine squared theta. Guess what that is? 1. So I just converted r squared into rho squared sine squared phi. That's r squared. Let me go back over here. What am I doing? I converted z into this. Now r squared is rho squared sine squared phi. You know, we like to solve for rho. I mean, you know, when you get an equation in rectangular coordinates, sometimes you like to solve for z. When you get an equation in polar, maybe, or cylindrical coordinates, you like to solve for r, maybe. Maybe here you like to leave it in z. But when you switch it to spherical, maybe you like to solve for rho. I'm going to try to solve for rho. You know what I'm going to do? I'm going to divide by rho. That cancels it here. It leaves me 1 here. So cos phi equals rho sine squared phi. To solve for rho, I think I'll divide rho equals cos phi over sine squared phi. You know, this was a paraboloid, remember. Paraboloids are not too bad in rectangular coordinates. They're definitely not too bad here in cylindrical coordinates. They're not too nice in spherical coordinates. Cos phi over sine squared phi ain't that pretty. It's got some undefined issues on phi. You know what I meant? So I'm playing around, I'm converting, I'm playing with equations. I mean, this is kind of what you do to get used to going back and forth in these coordinate systems. So I'm doing a little of that. You need to do more than I do. A lot of it falls out of this picture, but a lot of it is just a lot of cool equations. You can look them up in 11.7 equations for converting back and forth. You know, so one of the things, when I first introduced this coordinate system to you, I didn't ask, I mean, are you convinced that it works?
Yeah.
I mean, can you get anywhere you want to get in space with this coordinate system? I mean, if I want to hit this spot in this room, you know, when I'm in this room, I want to hit this spot. That's a dot. That's a point. I know it's free. I want to hit this point. There's a point in this room, and how do I hit it? In X's, Y's, and Z's, I go out X, over Y, up Z, and I hit that spot. Okay. In spherical, what do I got to do?
Turn towards it, look up at it, and then walk to it.
Okay, so, right, so I'm at the origin. It puts me off camera. But when I'm at the origin, you're right, I rotate theta. That makes me look at it. And whatever. I need the distance from the origin to that point. That's rho. I rotate rho, that angle theta, but then I also got to rotate it down from the z-axis, this angle phi. And I can hit that spot, given a certain, I rotate theta, I rotate down phi, and then I walk out that distance rho. Right, I mean, I don't know what the order is. The order is rho, theta, phi. But it works. Now, and there's, just to mention one more thing here. So it turns out that the phi, well, if you're going to let theta kind of go all the way around from 0 to 2 pi, like theta does, then you don't need that much phi. You only need phi to go from 0, and again, this is funny, pointing straight up is 0, to 180. You don't need phi to go down to 180 and back up the other side, because theta will get over to that other side for you. So typically there's kind of some thoughts here that say that theta gets to go between 0 and 2 pi, but phi doesn't need that much. Phi just needs 0 to pi. So we're back in 11.7, messing around, learning about these new coordinate systems. There's some homework assigned for this. You should probably work on it. Eventually what I'm trying to do is get back to triple integrals, okay? I'm trying to get back to triple integrals in these new coordinate systems. That's where this all culminates, and then this chapter 14 is over. So it all culminates back in triple integrals. But let's just keep playing with the coordinate systems for a second. You know, one place they're useful, this spherical coordinate system is pretty awesome. So if you're walking around a sphere, the spherical coordinate system might work good. You know, we live on a sphere, sort of. The Earth. It's not a perfect sphere, but we can pretend it's a sphere. Check out this picture here. So this is the Earth. And this could be the North Pole here. By the way, the radius of the Earth, so if we're on the surface of the Earth, the radius of the Earth is 3,960 miles, roughly. It varies a little. But, so I'm saying if we live on the surface of the Earth, our rho from the center of the Earth out will be 3,960. And then the theta and the phi are related to, they're not exactly, but they're totally related to latitude and longitude. Let's have a little discussion on latitude and longitude. If this is the equator, actually the Earth's tilted, you know, but if this is the equator, we call that latitude 0. And if you live in the northern hemisphere, then that would be 10 degrees north, 20 degrees north, 30 degrees north. Ocala is roughly 30 degrees north, 28 degrees north, or something like that. Where's the North Pole? 90 degrees north, right? That's the latitude of the North Pole. Not much of a latitude, it's the North Pole. You know, below in the southern hemisphere, 10 degrees below the equator is 10 degrees south latitude, 20 degrees south latitude, all the way to the South Pole, 90 degrees south latitude. So that's latitude above and beyond. And so that's sort of phi. But you know, phi is measured from the North Pole down. So if I said, oh boy, hang on. So here's England. Here's France, Spain, Italy, Israel, Africa, Arabia, Iran, Iraq, China, Vietnam, Denmark, Iceland's out here, Russia, roughly. What am I trying to say? So I'm trying to say that if I lived in North Africa, that might be like here, that might be like 20 degrees north latitude. But what would be phi? If I said I'm 20 degrees north latitude, what is phi?
70.
Good, because phi is measured from the North Pole down. So phi, so latitude ain't exactly phi, but latitude can get you to phi. Latitude would be, you're right, if you're 20 degrees north latitude, then your phi is 70 degrees, right? From the North Pole down. That's how phi is measured. Longitude is measuring around the Earth like this, and so there's 360 degrees longitude, or starting at 0, which is where the x-axis is, right? 0 degrees is where the x-axis is. On the Earth, that's through England here, through Greenwich, England, through France, through North Africa there. That's what we call 0 degrees longitude. Florida, you know, across the Atlantic over here and over here, Florida's about 70, 80 degrees west. You know, Germany, Moscow, that's 10 or 20 degrees east of what's called 0 degrees longitude. And I'm suggesting that that's where the x-axis is, because 0 degrees on the x-axis, 0 degrees theta is the x-axis. And when you rotate east, that's 10 degrees, 20 degrees, 90 degrees east. So like I'm saying, if I'm in Germany, it's 10 degrees east. What's my theta? So 10 degrees east longitude. What's theta? Theta is 10 degrees.
Okay, so it would be
But
350 or something.
But Ocala, or Florida over here, here's Ocala, way over here across the Atlantic, is 78 degrees west longitude, maybe 78 degrees west longitude. But that's, here's the x-axis coming out at me. I'm rotating back from the, what do we should call that negative 78 degrees for theta. Or 360 minus 78. What's 360 minus 78? 200 and 360 minus 282?
Yep.
282.
Faster than a calculator.
That's right. Faster than a calculator. Or 282 degrees.
Yep.
So there's some interesting problems, and I may even come up with a problem. There's some interesting problems walking around the Earth, thinking about latitude and longitude, how it relates to spherical coordinates. On the surface of the earth. And basically, it's, if you're on the surface of the earth, your rho is this, so rho isn't changing. And latitude and longitude are related to phi and theta. Not exactly phi and theta, but related to phi and theta. Right, right. And there's some problems in the book kind of make you do that. I might make you do some of that. All right, so just to get back to triple integrals before this, I mean, I'm going to end class here in just a second. But so here's what happens. We get back here and we can integrate. We can do triple integrals. So, you know, I can do a triple integral in dz, dy, dx, you know, and I can get volume using a triple integral. And this thing here is my dv, you know. That's my dv over a solid S. Okay, I'm integrating over a solid S. All right, well, if I want to do this in cylindrical coordinates, let's see what changes. I got, oh, dz, dr, d theta, right. The r's and thetas instead of the y's and x's. Oh, but keep in mind, when you go to r's and thetas, they bring in that extra r, don't they? Remember that? So we got, remember it was r, dr, d theta. So if the r shows up, r, dz, dr, d theta. That extra r coming from the dr, d theta. So here I am in what you call cylindrical coordinates, doing a triple integral in cylindrical coordinates. Okay, that's the dv. Okay, triple integral in cylindrical coordinates, triple integral in rectangular coordinates. By the way, cylindrical is nothing, man. It's just taking the x's and y's and turning them into r's and thetas. It's got this new name, cylindrical, that makes you think it's something new, but it's just a good old polar kind of. 3D polar. Polar with a Z, you know? But now, triple integral in spherical coordinates, if you're trying to do volume, the dv, you get this. Rho squared sine phi d rho d phi d theta. That's the dv. That's the dv. In other words, you know, this had this, oh, this has this extra little r that comes with it. Well, this has a bunch of extra stuff that comes with it. A rho squared sine phi comes with it as part of the integrand as well, as part of the dv. It ends up being part of the integrand. But then you're moving different, man, you know, when you're in rectangular coordinates, you're moving out and back and left and right and up to bottom and top to bottom, and you know how rectangular coordinates move, you know. But now you're moving, rho goes from the origin out, phi drops from, I mean, this is this is new thinking. It's a different way of thinking, this new spherical coordinate system. Let's just try something. You know, the other day, I think I actually did, I did the volume of a sphere. I think I set it up, I did a volume of a sphere, and I think I set it up in rectangular coordinates, and we quickly realized how bad that sucked, because we had these square roots of these nasty, and so we used that as a catalyst to switch to polar. And then it was a lot better. But dude, what if we're in spherical? I mean, check this out. Can I find the volume of a sphere? Let's say I got a sphere here of radius A. How do I find the volume of a sphere using a triple integral in polar coordinates? I mean, not polar, sorry. I gotta talk too fast. Spherical coordinates. Well, I'll tell you one thing. If you're going to do volume in spherical coordinates, what goes in here? Well, you might say just a 1. Just a 1 goes here. Yeah, you're right. The 1 dv. Okay, so now the dv goes here. So what's the dv? For spherical coordinates, the dv has got some shit attached to it. And the dv is this. Right. Rho squared sine phi d rho d phi d theta. By the way, I suppose you could switch these in any order you want, just like the x's, y's, and z's. But we tend to stay here. This tends to be a good one, I think. Anyway, if you're on a sphere of radius A and you're trying to find the volume, you let rho go first. Rho is a variable that goes from the origin out. Rho goes from the origin out. There's an example of a rho, stick of rho going out. What would be the bounds for rho?
From 0 to A.
That's right. You might say, well, wait a minute, man. The name of this thing is x squared plus y squared plus z squared equals a squared. That is the name of that thing in rectangular coordinates. We learned a few minutes ago, and learned a lot of crap here, but a few minutes ago we learned that in spherical coordinates, what's his name?
Rho equals A.
Rho equals A. So rho goes from 0 to A. Hey, that's awesome. How about phi? How would you like phi to move here? Let's see, phi.
0 to pi.
Maybe I need to get phi to go all the way down. 0 to pi, right. Starts here at 0. That would be half a pi, and down there would be pi. I probably should let phi go from 0 to pi, and then what about good old theta?
0 to 2 pi.
All the way around should do it, huh? Should do it. Yeah, this ought to work, I suppose. If I do this triple integral in spherical coordinates, that means I'm integrating with respect to rho. Can you just help me? How do you integrate with respect to rho?
Ignore sine, well, not ignore sine phi, but treat it as a constant.
Treat this like a constant. Yeah, you're right.
And then, well, do the power rule for integration of rho squared into, well, that.
Yes, thank you. Right, do your power rule, 1/3 rho cubed. This remains constant. You're right. From 0 to A, plug in your A. Now you're integrating with respect to phi. Good luck on that. Then you integrate with respect to theta finally. In the end, I suppose this answer ought to be 4/3 pi A cubed, right? The volume of a sphere of radius A. So that might be a fun little proof. It's not hard to integrate, but you got some work to do to finish this. Yeah, you can already see the A cubed coming in there. Anyway, that's enough. A little taste of where we're heading and where we finish this chapter. Triple integrals in these new coordinate systems. But first, you might want to get used to these new coordinate systems in 11.7. So I will quit today. I think we'll do it. I think we're doing a quiz this Wednesday. And probably our test is next Wednesday, right before Thanksgiving. That's it. That's it.